Please take your seats. We are starting now. How's your lunch? Please don't fall asleep, and I know the back chairs are a little bit more comfortable. So please give your attention for all these presentations. We have our first presenter, Ali Bassam. So he'll get the first bell at 10 minutes, and then the second bell you will do two bells at 15 minutes. Okay, good luck.
Doing so at the receiver, with match filtering, which gives us an equivalent channel of UV, I receive samples, signal samples to take this form. The DFT is divided by data, and the estimator is based on finding the centroid of each byte. So, like how we saw before, we have 8 bytes. So if we just disregard the what I'm trying to do is computing the centroid, which is the center, basically the center of the visual spectrum on each byte. And then after finding the centroid, which is the same as finding the buffer shift on each byte, I average the results out to get an average. But then one problem here is what kind of, where do I start my estimation for each byte? Because I need a starting point and a stopping point for each byte to carry on my summation for my estimation. Well, the best range that I could find was around the middle, or around it. So the starting point would be the midpoint of each byte, the starting point would be also the midpoint of each byte. So I found this to be the best window for estimating the centroid. Again, also I chose windows such that both forward shifts and backward shifts are accounted for. And of course, there is a limit to how much shift this window can handle. But what we do know from underwater acoustic communications is that typically A is on the order 10 to the minus 3 and 10 to the minus 2. So that means my estimate, the way I designed it right now, is it can handle up to 29 knots of, let's say, some rate speed. So I ignore the first part because it just makes the design for the estimator simple. Because to find the centroid on the first part, we need to use circle configuration. So I just really love the example. The estimate, as I mentioned, also after finding the frequency shift from each part, I average out the results. Now, once I put all these points into consideration, I'll get this expression. And sorry, the summation should be out slide. So I'll give this operation. This summation right here is the simple computation of each byte. And these are the limits that I talked about, where I got my centroid estimation for MR. MR is the original location of the bytes. So by subtracting these two, I get the shift. I get that positive result from the buffer. This sum is what averages out at. And these are the parameters these parameters show as non-negative because this operation by itself will give me a discrete time shift, which is A times FC times DS. So I just divide both sides by FC and DS. My estimate. So further analysis reveals from the endpoints that I chose for the centroid is that I have to observe this limit at all times. So this is kind of like a design criterion for my estimate that I have to choose a number of bytes, the carry frequency, and the sampling duration in such a way that it's always less than half, less than 1 over the maximum Doppler scale in my channel. So I take into account Doppler scales up to 10 to the minus 2. So that would mean I'm observing this bound for n estimators less than 50. As long as I'm observing this bound, I'm guaranteed to complete estimate. So now that A is known, all I have to do now is compensate. So the first thing I need to compensate for is dilation and compression that occurs in my signal. And I do that by resampling because from DSP, if I look at this as a space-time domain, 1 plus A times NTS is the same as resampling my signal by a factor of 1 plus A. So since I have 1 plus A in my 1 plus A times C, I need to resample by 1 over 1 plus A factor. So get rid of the sample drift. I get rid of the compression of the vibration in my system. Now, since I resample one plus A hat, my carrier frequency offset goes from AFC to AFC divided by that number. So I backshift, or I compensate for this shift by A hat FC. So I use my estimated A backshift. So this is a similar model that we're working on. This is what we see here is just what we see here is the frequency domain while the signal get right, the frequency does not remain. This is just normalization. I circulate up and through. This is the double channel. I go through a noise channel. Then I receive it down to the decibel. So I get it back to the sweep time at this point. So this one goes from discrete to continuous. This one goes from continuous to discrete. So this is where my estimator does its since my estimates of the frequency domain, I take my signal, goes to the frequency domain, do my synchronic calculation inside it. Then after comparing it with the actual frequency, I can resample. So I resample my received signal by the estimated A hat. So I use this estimated A hat by so the output just have some data that was just resample data. This is resizing. So the output I actually present is resizing for it because resampling can change the duration. So this output is resized back. And this is where I do my compensation. Again, also my compensation is frequency because I am trying to back it very quickly. So I did various tests on different values of A, but I'm showing here is for A equals to minus 2 over 6 here. So what you see here is what I receive as a baseband. The received file is sequence as a baseband. You can see that the first file is what the second, third, and fourth will also be shifted by a certain amount. But as we progress through the file, that shift will not be consistent. So yes, this was shifted from here to previous samples. This might also be shifted also by 52 samples. But then as you go at higher frequencies, that shift of 52 samples might go to 53, 54. That depends on how erratic the filter effect. This is after resampling. You might not notice much of a difference here, right? But that's because the breadth in samples, so that difference 52 goes to 53 and 54 at around this range. So I am drifting by 1 to 2 samples as I progress. So that's why you can't see it on this scale. You can't see the resampling, the result of resampling definition. Because it's just 1 to 2 samples on each one. And this is after backshift, this is after double compensation. I bring more by the so this is after compensating for the resampling. And this is compensating for the double back. So this will get after checking the table, you will see that estimated file sequence and achieved file sequence are from the same position. The difference is amplitude. The UPU affects one is normalization and the other is has to do with the resampling itself because the samples go
Thank you, Ali. Any questions for him?
How do you expect the signal-to-noise ratio of your channel noise to relate to the variance of your Doppler estimate?
The signal-to-noise ratio is related, is direct, it's proportional. So the Kramer-Rao bound is proportional to my SNR, because what we do is we try to compute the Fisher information matrix to get the Kramer-Rao bound. The Fisher information matrix itself is inversely proportional to the SNR, or the noise variance from which you get SNR. So the Kramer-Rao bound is inversely proportional to the Fisher information, which means it's directly proportional to SNR. So once I know the SNR, and once I know the remaining parameters for my Fisher information, I can get the bound.
Thank you. Any other questions?
So you said they will be shift out in carrier. So when you filter out your carriers, do you use two?
No, when I filter out the carrier, the frequency object will remain. It will not be mitigated by the Doppler. So the Doppler shifts the frequency by a value AFC. The Doppler converter only down converts for FC. So AFC remains. We can't down convert by FC because we remain. So we are forced to down convert by the same carrier.
We'll take one more question.
You have the OFDM signal. So why you are constant and A is constant? So it is significant.
Right. A does change with, that's right. No, A is constant, but the shift at each carrier can be different. And true, A can change, but A can change on the path, which depends on the environment. But I think the information is an environment where A is fixed, and I'm only taking one single path. I think A depends on the environment. But now, for each carrier, the OFDM signal shifts different.
Thank you, Ali. Now we will have a presenter. Ali Fituri. Good luck, Ali. You have 15 minutes. You will get the first bell at 10 and then 2 bells at 15.
Good afternoon. My talk today is about zero-emission hybrid microgrid optimization. First, I would like to go over the outline, the notion of microgrid, the tidal energy modeling and optimization. Then I will go to the case study, which is ferry charging station, storage units, optimization and power quality, renewable energy integration, and I will conclude with the summary and talk about the prospects. So first, what is the microgrid? The microgrid is a domestic and limited energy system that contains distributed resources and loads and optionally storage units. Why we need the microgrid? We need the microgrid because it's enhancing the efficiency and it guarantees more contribution for renewable energy, and it also increased the reliability and sustainability. The microgrid components, distributed generators, according to IEEE design guide, the distributed generators defined as generators or storage units that not directly link it to the main transmission system. And loads and storage system controllers, interface point. Here we can see the simplest microgrid with a single distribution resource and ability to connect to the main grid and work as isolated as well. Advantages and disadvantages of microgrid. Advantages is on the top of advantages is the isolated mode. It can isolate itself from the main network, and then the ability to control the load during the peak time by demand side management. It could be decreasing the consumption during the peak periods, or even selling electricity back to the main network. More contribution of renewable energy. The disadvantages or drawbacks of microgrids is related to interface challenges. It requires more space because of the storage, the need of the storage unit. And also it needs regulation in the policies and standards as well. So the main source in this microgrid, or the suggested microgrid, is tidal energy. Tidal energy is just one image of ocean energy, which also include ocean waves, ocean currents, and thermal energy. So what is the tidal energy? As you can see here, is the kinematic of tidal energy. So as the tide comes and goes, it rotates the turbine and generates electricity. There is a huge opportunity for clean energy from the ocean, but unfortunately it's not all available, or there is a limited amount of energy could be harnessing from the ocean. We are talking specifically about in-stream tidal energy, and there is also a limitation of, despite the fact that the tidal energy is the most promising ocean energy, but it also has some limitation, like the cost. It costs much more compared with solar and wind energy. It requires certain sites in terms of depth and speed aspects. There are challenges on control strategies, mechanical obstacles, optimization and uncertainties, and storage units. So next we are talking about tidal stream turbines. There is two main types of turbines here: horizontal axis turbine and vertical axis turbine. We are talking specifically about the micro turbines, and micro power, as we are suggesting the the smart microgrid. So we can see the mathematical model that used to calculate the maximum power, available power versus the extracted power. And here is the prototype of the micro turbine. Turbine optimization, which is the core of my work, how to make optimization by using these turbines. So we are not talking about single turbine. Clearly, one turbine is not enough for power production, so we are talking about sort of turbine farm. We are looking for the ways how to rearrange those turbines in different layouts. Here is statistics from the comparative studies, and it shows the relationship between turbine number and the number of turbines and the extracted power. So as you can see, it could be increased to some point, but after that it might be decreased by increasing the turbine number. So there is a limitation here in the numbers. We are talking about different layouts, the position of turbine itself, the tracking angle, all these sort of things. Installation and maintenance also, as we increasing the number of turbines, installation and maintenance cost becomes much more. Here also is statistics from the same source, and it shows the relationship between, here we are arranging the turbines in rows, and as we increasing the rows, the time average power increased. There's different values of different blockage ratio here. Now we are switching to the other side, we are to the flip side, and think about how to go green in the load side. So my case study here is Halifax ferry, and on the top of the consideration is pollution. We have statistics here from Halifax Municipality Report 2010. As you can see in the pie chart, the electricity poses the most significant portion of the emissions. Also, the table down shows the source based on the emissions based on the sector. The vehicles fleet here has 34,538 tons of CO2 emissions. That's only in 1 year, 2008. So the ferries poses 5% of this. 5% for 2 or 3 ferries is not few. So that's a considerable amount of emission. I'm planning to work on the trip scheduling and how to arrange the storage system, located them in different locations, and try to get them optimal charging time by locating or relocating them. I will also think about the power quality parameters, active and reactive power, voltage, frequency, and how to work with them. So as I mentioned before, the main issue with tidal energy is the high cost. So it costs much more than other renewable energies. So we think about reducing the cost, how to reduce the cost. One of the categories to reduce the cost is optimization. As we maximize the power, then in turn will reduce the cost. And there's another way to reduce the cost is by integrating more renewable energy with the tidal, such as solar energy and wind energy. Wind energy looks similar to the tidal energy technology. It's inspired by wind energy, and in some cases it uses the same controller strategy, because both are rotating. Of course, there's different in terms of speed and the fluid density or the space density. Solar energy could be used as a backup power to use for utility, or even when we face problem with the main microgrid. There is also a possibility for load banks, like for night time. We may think about street lights as a load bank. So in summary, the main idea of my research is modeling and optimizing microgrid. This microgrid supposed to be literally zero emission microgrid, and it could be either grid connected or isolated from the main grid. It also include the hybrid microgeneration system like tidal, wind, solar, or maybe more. The specific idea here, as we rearranged the turbines, increasing or maximize the power, hopefully ending up with a way that no one have done before. The prospects of the work, grid connected state, so all the previous were talking about islanded modes. Diverse green energy sources, more renewable energy could be included. Combined heat and power, so heat could be included in the system in order to reduce the cost, or the overall cost. Electricity vehicle is also a huge area for research. So this is my references, and I almost finished my presentation. If there's any questions.
Thank you, Ali. Any questions for him?
Yeah. So this is about the ideal case. So the realistic case definitely is different. It may has or involve more constraints. So this is will be covered in the future study, I guess. Yeah. For I also have storage system calculations and all this sort of things. It's coming research. Yeah.
Thank you. Any other questions?
So you said that in order to optimize your unit or your unit and whatever it is, you will run in a maximum power, right?
Yes.
So in maximum power, you will put all those components in stress, so you will have the highest failure. So as the gentleman mentioned, so the reliability and stuff also kicks in. So how could you make up for that? So how is optimization be effective if
Okay.
reliability is in question?
I guess I didn't say maximum power. I'm talking about maximized power. So try to harness it as much as we can.
Thank you. We'll take the last question. No one else? No more questions? Okay. Thank you, Ali. We have our next presenter, Al-Roomi. Good luck.
Thank you. Good afternoon, everyone. My name is Badr Al-Lahida, and today I'm going to present my. I'm going to talk about using artificial neural networks for solar radiation forecasting based on meteorological data. The presentation will cover the objective of this work, then a brief description about solar energy, then about the artificial neural networks which is used in this study. Then I'm going to talk about the proposed model and its simulation result and compare it with similar models. Then at the end is the conclusion. The objective of this work is to find a model that forecasts solar radiation by using a simple artificial neural networks which means less number of neurons, layers, and inputs. Also trying to find the best set of weather variables as input, with the objective to reduce the error of the proposed model. Before talking about the proposed model, I'm going to talk briefly about solar energy. Solar energy can be defined as the energy proposed from the sun's radiation. I'm going to talk about solar radiation atmospheric interaction. There are 4 types of solar beams due to interaction with the atmosphere: reflected, absorbed, scattered, and direct. Scattered and direct are the most important factors in solar power application and forecasting, and they can be expressed by this equation. So the global horizontal interaction, horizontal radiation equal the diffused plus the direct times the zenith angle. The Earth solar radiation distribution intensity is shown in this figure, and you can see the more yellow and bright is the more radiation, and the black or the dark color is less radiation. And to harvest this radiation, there are two ways. First one is thermal, and the thermal technology it's focused the sun's radiation to generate heat, and this heat can be used directly or spin a turbine, or use the heated water to spin turbine and generate electric energy. The second way is the photovoltaic. The photovoltaic cell made of semiconductor material which converts light into electric energy. And the most common method used is the photovoltaic. Solar energy has many advantages. Nothing is consumed to use this energy, does not damage the environment, can be constructed close to consumer, which leads to low transmission and distribution cost. Also helps societies to achieve political and economic independence. However, solar energy has drawbacks. It's intermittent and variable, which result in power fluctuation. Also, it has high initial cost, high initial installation cost. Next, I'm going to talk about the solar radiation forecasting. Solar radiation forecasting helps to market and manage the generated energy. Also helps to size the PV systems. Solar radiation can be forecasted using artificial techniques such as artificial neural networks, ANN, genetic algorithm, GA, fuzzy logic, or hybrid system, which makes more than one technique. The most common technique is the artificial neural network, and it can model, because it can model complex and nonlinear systems. For this work, I used artificial neural networks. And artificial neural networks are designed to do a specific task through a learning process by providing the input and the output data. The ANN finds the relation between the input and the output data. Artificial neural networks, or ANN, are divided, consist of three parts: input layer, hidden layer, and output layer. This figure shows a simple diagram of artificial neural networks, which has only one neuron. If we add more than one neuron, we'll have this figure, which is considered or called one layer. And if we add if we add more layers, we'll have this structure which is called multi-layer neural network. The criteria to evaluate and compare between different models, different AN models, is number of layers, number of neurons, performance evaluation, such as odd mean square error, mean absolute percentage of error, and coefficient of correlation. In this section, I'm going to talk about the proposed model and its simulation, and the simulation and compare it with other models. For this model, I use different meteorological data. I use air temperature, relative humidity, pressure, cloud cover, vapor, wind speed, and direction, and the day. And this work is divided into 3 steps. Step number 1 is finding the best combination for weather variable that give best GSR prediction. Second step is building the proposed model based on step number 1. And the last step, or step number 3, is compare it with other models or similar models. Step number 1 can be divided into like 3 sub-models, sub-steps. Sub-step number 1, using only one weather variable. Sub-step number 2, using 2 weather variables. Third sub-step is using more than 2 weather variables. For first step, using only one weather variable, so I used all the 9 or 8 weather variables. So here is the models, 7 models, and here is the input: day with cloud cover, day with humidity, day with temperature, day with vapor, with pressure, with wind direction, wind speed. And here is the number of neurons that give the best result. And here is the performance, root mean square error, mean absolute percentage of error, and coefficient of correlation. And you can see that the best input or candidate is the cloud cover, then humidity, then temperature, and so on. The sub-step number 2, I use 2 weather variables. I use there are many models, but I choose the best 4 models. So the best one was has humidity and cloud cover as inputs with the day. The next one, or the second best model, has temperature with cloud cover. Third one, temperature with humidity, and the fourth one, cloud cover with vapor. The third submodel in step number 1, or the sub-step number 3, using more than 2 variables. So here, the first model has, of course, better result. As more input variables, we get better results, but more complicated model. So this is step number 1. Step number 1 is comparing or finding best weather variable. So I can conclude that cloud cover, humidity, and temperature are the best candidate for radiation forecasting. However, cloud cover was excluded because the cloud cover is difficult to be predicted. So I excluded the cloud cover. So I left with air temperature, humidity, and the day as input for the proposed model. And here is the model that I used. So divide to 4 models. Submodel number 1 use day radiation and day humidity and temperature. If one of the humidity or the temperature is unavailable, there is is submodel number 2 to predict the temperature, submodel number 3 to predict the humidity from previous data. The last submodel, then submodel number 4 use the predicted values to predict the solar radiation. So for submodel number 1, here is the output. So the input is the temperature and the humidity. So I used 75 neurons, and here is the performance result, root mean square error, mean absolute percentage error, and the R, coefficient of correlation. Here is comparing the actual with predicted data, and the blue one is the predicted data. And here is the fit between the actual and predicted data. And the last figure is the performance. So here is the root mean square error, mean absolute percentage of error, and coefficient of correlation versus number of neurons. And you can see it's like the best one is almost 75 neurons. When I use 75 neurons, I get best result, minimum errors, and high coefficient of correlation. For submodel number 2, predict the temperature from previous data, day and last year temperature, humidity, and radiation from the last year. The result is not too bad. So here is the performance, and here you can see the predicted and real data, and here is the fit between predicted and the real data, and here is the performance. And at around 151, we got the best combination. Here is to predict the temperature, the humidity, and you can see at almost 130 or 135, I get the best result. The last model that used predicted data, predicted temperature from previous year, and from submodel number 2, predicted data from submodel number 3, and I inject these to submodel number 4, and here is the results for 1 year. And the last thing, comparing my work with previous works. So here is my work, and with previous work, people used like different input weather variables. So here is the inputs and number of layers, number of neurons, and performance. I can conclude that a new model for GSR prediction using ANN was proposed. The model used most effective weather variables. There is no relation between number of neurons. The number of more neurons does not mean more accurate model. Thank you.
Thank you, Badr. Any questions for him?
Thank you for your presentation. How you came up with your network models? Did you have some regression logistics to train your network, or how you propose these networks for you, or just like
How to what?
you propose some networks, right? Different layers, different nodes.
Okay, yeah.
So how you came up with these networks?
Okay.
How you
how-
choose them? Have some training or
Here's the neural networks. The function here function here is play like the most part. So here is the input, but I played with the function, and there is like many functions used for prediction here inside the neural networks. And some functions are good for like prediction, some are good for different criteria. So I pick like the most common function that's like the best for this kind of prediction, and I use trial and error. Like I tried with like different combination, different number of neurons, different number of layers, and yeah. So this is how I achieve my
I'm asking that because this is usual to use machine learning stuff in, building your network, neural network. Usually, do some normal, regression logistics to build up your network and find the optimal network. I was interested to know whether you used some, investigations in machine learning methods to come up with the best network you can get.
No, as I told you that I use the most common, which is like the literature function, the best function that you like used in prediction, and it's difficult. It's trial and error. Like even the artificial neural networks, sometimes if you run it again with like some of the neurons, you might get different results. So.
Similar, works in this area?
Yeah, here's like the last one is my work, and these are like from the literature, but some of them they use like different variables. Some of them they use like more variables. Some they use like sunshine variation, like different variables. But in general, the aim of this work is to have like simple and more accurate model. So I tried to not use more inputs because the system will be sophisticated, and I need like more like faster prediction. This is the aim of this work, to have like simple model. Thanks.
Thank you. Any other questions? We'll take one more. Okay. Thank you. We have our next presenter, Khalid Ahmed.
Hi everybody. First I would like to thank all of you for giving me this chance to stand in front of you. My presentation today about the speckle tracking echobiography. As all of us know about the size of your fist, human heart is the most important muscle in your body. And this muscle could beat 200,000 in one day and could pump more than 2,000 gallons of blood in your body. the single cycle of heart activity, it can be defined two basic phases. First one is systole, and the other one is called diastole. Systole, when the heart pumps the blood to your body, and diastole, when your heart relaxes. So, since the heart is very important, and if the failure of your heart will affect all of your cells in your body, so it's important to have the proper tool to monitor and evaluate the work of our heart. So one of the important tools that we use in the clinic to evaluate the heart is echocardiogram. It's echocardiogram uses sound wave to produce video image. And through this video image, the doctor can test and follow the size and the shape of your heart and distinguish between the failure result from the systolic cycle or systolic cycle. Sorry. Here on the right side there, you see just one frame of the feed. From this frame, the specialist would like to go frame by frame to choose the best frame when your heart start, for example, the cycle of systolic, and he go to the border or the wall of the left ventricle, for example, and select some point there which have his own pattern, and then they go to the frame after and try follow this pattern and go frame by frame to figure out how this pattern is moving, how the distance change between two patterns, to get some parameter to describe how your heart is working. So all this job is done manually and depending of the experience of the doctor, and it's time consumption because it takes a lot of time to do that. My goal is to decide to make all that done by computer by using image processing. So, for example, here I show you on the right the left ventricle. Here, the left ventricle microtium undergoes a complex deformation, and we could divide this deformation in 2 and 3 different strains. First one, longitudinal, and the second one radial, and the third one is circumferential. So the left ventricle, they have 3 different change of the shape. One of them, they change the length of the length or the longest of the left ventricle itself, which measures the distance between the base and the bottom of the ventricle. The second one, there is a change in the thickness of the wall for the left ventricle itself. And the third one is called circumferential strain, and is defined as the change of the radius in the short axis perpendicular to the radial and long axis. So here, as you see in the left there is a small square, and that square they have unique pattern. So the doctor, he was going to choose that square to define the location of that square, and then they were going to follow it part by part, frame by frame. For example, if we go close to that image, and you can see here, in the bottom there's just 4 by 4 pixel, and I would like to find that in all that image here. This is not easy job, because now we're going to go to the first row, the first 4 by 4, and then we're going to shift the 4 by 4, shift to the one after, and every time when I shift, I would like to compare. Is this what I am looking for? Is this the 4 by 4 that they have at the bottom or no? So that means we're going to go through all the, if this 250, for example, pixel, if this 200 by 200, that means we're going to go first 4, and then shift 1, second 4, and then shift second 4, and then we're going to go down the second row, and we're going to go through all of that. This will gonna be is not a good way to find my target, to find the best matching. Here, just I will show you some of the technique we could use to find the matching. We have here two frames. You see the car in the two frames. The current frame, the previous frame, you see the tires of the tire. That tire, sorry. In the frame at the top here, in the frame at the top there, you see the tires at in the second, it's in the second, in the bottom in the second square on the right. And in the current frame, the cars move a little bit, so the tires move to the fourth square. But in the background, both of them is constant. There is no movement in the background. So what we're going to do first is to change it from the color image to the black-white image. So it makes it more easy for me to search for my target. Because when I work with that color, that means I will work for the yellow, and the yellow to go from white to dark yellow. And then we're going to search for red. Also, we're going to search from dark red to white. So why I keep all the color? We could change the image to white, black and white. So now what we have white, we have black, and we have between them. So I will thinking how we could find that the movement, follow the movement of the tire from the second frame, move there to the fourth frame, to the fourth square. So rather than go to search from the top, the first square on the top, and go square by square by square, we could do other things. Since when we take image, when we take video, we have limited to frame per second. For example, for ultrasound, we have 25 frames per second, and could go maximum to 60 frames per second. That means no matter how much my object is moving very fast, because I have multi-frames in 1 second. So in the end, when I get 2 frames and compare with between them, the object just moves a little bit. So rather than go to search in that, and then I have object in this current frame. I'm looking for the previous position for that object. Rather than to go to all position that are previous frame, why you don't go just, if I have object in the position number 4, let me go back to the previous frame and go to the position number 4. Start there. Is it used to be there? If it's not there, let me go around searching. If it's not there, let me go wider, rather than go start from the top one by one. So here, as you can see, we have target block, and so we're going to go to the past frame, and we start the search from the center of that object. And if it's not there, let me go around and go around. And how we figure out is it our object or not? Here, because with all what we have pixel, we have value of pixel run from 0 for 256, for example. So just we do small subtract between the value of pixel from this location minus the value of the pixel in the same location on the other side, the other next frame. Subtract all of them. If I would like to compare windows 3 by 3 or 4 by 4, I could use the main absolute difference. And by this, when I am searching for example, object have Windows 4x4 pixel, when I minimize absolute difference, that means I get close to my object. Other method we could use main square difference. In main square difference, the difference will gonna be big because 5 minus 2 different than 5 minus 2 square. So other method for searching is called hierarchical search. In hierarchical search, we have object in this frame. I'm looking for the same object in the previous frame to see if it's moving or not. So we're going to go back to the same location in the previous frame and just search in that location and search for as we did in the first one. Just I go to the same position and other 4 windows around, search there. Which one is more matching to my target. If the second one there, the top one is more close to what I'm looking for. So I move my search area to that, and then I put other 4 windows around and compare all the 5 windows. And the second one, if it's the close one, the one on the left and the right, I go close every time. So I start search in this center and 4 around. Which one is close to my object that's searching? I move to that one and put other square around and search. And when my centers became the closest one, just reduce the step rather than go to 4 steps farther. Just go to 2 steps farther until I get my object. What benefit I will get from that? From the image of left ventricle, we looking for example, we need some information about the wall of ventricle cells, the wall of ventricle. So I will looking for some pattern in the wall itself, and I will gonna mark this pattern in first frame, and then I will gonna follow them the next frame and the next frame and measure the distance between them. What the change of the distance between them is the strain, and strain is defined the fractional change in the length of microtel segment relative to the baseline length. So all the time we're going to measure the distance, and this is called the strain, and also we're looking for the gradation between change of the length of the time, the end of the time, which is called strain rate. Here, for example, the first one in the top, I have 2 patterns, one in the green and the other one in yellow. The next frame, you see both of those go close to each other. So I'm going to follow them frame by frame to figure out how the strain between them. Here we have, from that we could get the velocity, the displacement, strain rate, and the strain. And the relation between these 4, we could go from one to the other one. From the strain, we could go to the strain rate. From strain rate, we could get the displacement. My work was going to be, first of all, I would rather than use manual to detect this point and follow it frame by frame manually, I would like to use the image processing. I would like first in the image I have different objects, so I would like to focus on one of them. So to focus on one of them, I would like to select the interesting area. So I would like right logarithm to just follow, for example, this wall, this area of my image, ultrasound image. So this is the first thing I would like to work with. Second thing, after like when we take the picture, as you see, when we take the picture, automatically there's green sequoia around your face, which is because there is some movement in your face. So also when from ultrasound image, I would like to select area of interest, which is the left ventricle. And then from there, I would like to select the pattern I'm going to follow. I would like the computer to select this pattern and follow it step by step, frame by frame. And from the end, they give me some parameters to describe the heart. How from this parameter, I could figure out if there's something abnormal in the heartbeat or not. This is some of my reference. And thank you for attention.
Thank you. Any questions for him?
Actually, I have 2 questions. One, what I understood from your topic, group matching is used to. So, did you test the high level of noise with this technique?
Sorry?
Did you test your algorithm with high level of noise? So, did you take the noise in your consideration?
Yeah, the noise is very important here because we're talking about the pixel by pixel, and the noise, it's big serious here because we're going to affect the pixel itself, okay? So from the beginning, to get the ultrasound, the species, they have a lot of control before he record the video, because what he was going to do, he was going to record the video and then submit to the frame. So during the record of the video, he able to control a lot of parameters to make the video as clear as much as he can. So he was going to reduce as much as he can, because for me, if I take that frame and try to remove the noise, sometimes we're going to kill some of the bits, we're going to affect my so the first step and the more step, during recording the ultrasound itself, he should play a lot of things to make sure that he give me clearest one. And because if I work with it later to remove the noise, sometimes we're gonna remove some pattern I need it later.
Also, what the evaluation parameter we use in this program? What the main evaluation parameters that are allowed to use?
For me till now, I just start working on the subject. It's all this area is new for me, okay? So I study a lot, I go through, but I didn't work to evaluate my work. It's going to be the last step to do, to evaluate my work with the other, because there's a lot of method to give you some information about the thickness of wall, the movement of wall. So we're going to, I just start now, I can.
Also, the main point for the application of medical image is to speed up the imaging process. So did you take in your account the time to speed up the imaging processing to get for getting less radiation? So did you get the execution time in your account?
Yeah, I should take, the time is really important. Otherwise, why we run out from the manual evaluation of this image? Because we would like to get the result faster, rather than spend 1 hour, go frame by frame by frame and zoom and take point and forward. It's going to be a hard job and take a lot of time. Its main object here, I would like to save time, that I will use the computer and image processor to make everything automatically. So rather than wait 1 hour to get the report, we should get the report in 5-10 minutes.
Thank you. Any more questions?
Thank you for the presentation. Your work reminds me the standard of MPEG video, the motion compensation H.264, I think. So there are many similarities as I studied the other subject. I want to know, is there any, have you had any thoughts about 3D model, or are you just working on 2D for now?
No, I just work about the 2D right now. Yeah. Because when we talk about 3D, we're going to be more harder to.
The challenge there that standard is that in 3D they have huge processing time, and that's the goal, result that we can get from it. Thank you.
Because also the first diagnosis they used 2D. They didn't go to the right away to the 3D, because the 3D just when they need it. But if you go to any clinic now and they would like to assist your heart, they just were going to go to 2D ultrasound, which is.
Thank you.
Okay.
We'll take the last question. Somebody has it? Okay. Good. Thank you for being in for the second session. We have a 20-minute refreshment break. There's tea, coffee, and cookies outside. And we'll see you guys at 2:30 for 3-minute presentations.